Hello and welcome back to the afternoon session of day one. So now Professor Tapomoy Guha Sarkar will continue his lecture on the large scale structure of the universe. Uh, so if you have any question, you can raise your hand or put your question in the comment or chat box. We'll put forward to Tapomoy Guha Sarkar. And followed by this lecture, there will be a tutorial session on the numerical analysis and body simulation. So please stay for that also. Okay, thank you. Now I'd like to request Tapomoy Guha Sarkar to start his lecture.
All right, so in the morning, we looked at the equation for growth of density fluctuations under several approximations. The first was we are looking at small scales. So we are following a Newtonian analysis. So relativistic corrections which occur on large scales, on scales of the order of the horizon, are not included. That's the first thing. The second is we are also looking at linear theory. So our fluid equations have been linearized to first order in the fluctuations. And the third is we have, for the time being, ignored any form of pressure. So we are looking at pressureless matter, so, or non-relativistic, or we are assuming very long mean free path. So when we have these assumptions, we saw in the morning that we can write the equations for the growing mode, or basically the density fluctuations, as this equation. Now, we looked at a algebraic way to solve this equation, at least in these approximations, and write an analytic expression for the growing mode and also the decaying mode, the two solutions, in the form of a quadrature, in form of an integral. So it's interesting that this was also done in a slightly intuitive way. So I thought it's interesting to again rework out that solution. It's the same solution we're going to reach, but the method is going to be slightly different. So I think this method is interesting and it's useful in our understanding. So Lemaitre originally observed this. So what his observation was that if you look at perturbation of a fluid with zero pressure. So again, we are talking about pressureless matter. So if you're looking at perturbations which are, say, spherically symmetric, so we look at spherically symmetric perturbations of pressureless matter, then in an evolving universe, if you try to understand what is happening, what Lemaitre studied, that these perturbations cause basically the evolution to mimic, like the shells which are expanding, to mimic basically modifications to the background evolution. So what does this mean? So it means the following. So let's say there are no perturbations. So then we have our homogeneous and isotropic universe, and we have a scale factor A of t, which is the only thing that we need to talk about cosmology. So that's the scale factor, which is known as a function of time. So this is, let us call this A background. And let's say this is a homogeneous background. So there is a rho background, right? So this is a function of time. So if you consider a spherical region, so if you look at a region and we assume that the perturbations are also are spherically symmetric. So what Lemaitre observed was that what linear perturbations do is that they of course that's a change in rho from rho b to some rho now, which is the actual perturbed universe. So this perturbed universe in the presence of, say, a spherically symmetric perturbation for pressureless fluid, it actually, what it does, it modifies this background evolution. So you can think of, this is another way of interpreting it. So it's basically a modification of the background evolution from AB, which was the original background evolution AT, to some new A of t. And these are slightly different from one another. So there's a slight modification to A when you change the homogeneous background to a perturbed background with a spherical perturbation for pressureless matter. And this is the crucial input of Lemaitre, which led Zeldovich to, and this is well discussed by Peebles in trying to attempt to solve this equation for the growth of perturbation. So basically, the presence of delta, which is a presence of fluctuations over a background, manifests as a change of the growing function, like the scale factor of the background universe. So this is the, and this is only linear theory, okay? So this is, and very restrictive, you just can't generalize it. So from the background AB, it's a modification to a new A, and these two background evolutions. So these are the two background evolutions, and I'm calling background because they are just A. A is everything that is there. Now the entire cosmology is in A, and A of t is different from AB of t up to first order. It's a tiny change. So we can write this A of t as A background of t times, say, 1 minus some epsilon. And this epsilon is, of course, function of time, and this epsilon is a small perturbation to A. So you can immediately see this is basically delta A by AB. Okay, so that is what epsilon is. Now, since we're looking in that region, it's a spherical region, we should then have rho A cube. Now, rho must be equal to rho background A background cube, and which basically connects the perturbation delta with the perturbation in A, right, through this. So you can now connect epsilon with delta. So that is very easy, because now you can write rho as rho background times 1 plus delta A cube, and A is A background cube times 1 minus epsilon, right? And that is equals to rho B AB cube. So from here you will see that delta will be equals to 3 epsilon. That's obvious, this 3 comes from here, cube. So basically what it essentially signifies is that we are now looking at the evolution of the universe with a new background, A of t, and that background is slightly different from the original background AB when your density was rho. So for A of t, Zeldovich would write just the Friedman equation, because it's just, you have forgotten perturbation, everything. Now you have a new background A of t. So A will satisfy the background equation. So you will have A dot dot equals to minus 4 by 3 pi g rho A. It's exactly what we have, the Friedman equation for pressureless. So now we have to find this A dot dot, and then you would have this A is basically related to A background. So if you write everything and you write rho as rho background times 1 plus delta, so you write all that, you substitute all that in, then you would have basically A background dot dot times 1 minus epsilon. That's the first term. Then you would have minus A background epsilon double dot, and you will have a minus twice A background dot epsilon dot. So that will come from the derivative of A. And on the right hand side, you would have minus 4 by 3 pi g rho background. Delta is 3 epsilon, so it's 1 plus 3 epsilon. I'm writing that times A background times 1 minus epsilon. And if you simplify this up to linear order, what you would get is, this is linear everywhere, in fact. So what you would get is, you know, A background, you also know that A background dot dot is minus 4 by 3 pi g rho background A background, and you have to substitute that. Once you do that, what you see is that equation, you get an equation for epsilon. So you get the equation for epsilon, which is, let me write it down, epsilon double dot plus twice A background dot by A background epsilon dot equals to 4 pi G rho background epsilon. So what is wonderful is that this epsilon, which is the variation of the A, the scale factor, satisfies the same equation as the growing mode. So all we need to do is now, if we know what epsilon is, then we know what D is. So we are interested in D. So they must be proportional to one another. They're related to one another. So delta must be proportional to epsilon. And what is epsilon? Epsilon is delta A by A. Right? So this delta A is the change of A. Now, what does A depend on? A depend on basically the cosmology. So if you remember how we solve the Friedmann equation, you write the Hubble's law and you write A. Finally, A, you can just see that A is basically a function of the different some initial conditions and of course on the omegas, right? So now let's consider a cosmology where you have only two kinds of stuff. You have omega matter and so omega lambda. So we are not keeping any kind of radiation. So that's crucial here. No pressure stuff. So omega matter and omega lambda. So then we can write down, we know how A depends on these quantities because we can write down the Friedmann equation. So let's write that down. So we have A dot by A whole square, which is H square. And this we know as H0 square times omega matter by A cube plus omega lambda, right? This is known, and we can integrate this equation and get A as a function of time. So this integration is crucial because now we are going to look not at A as a function of time, because that is something we know. We are interested in the variation of A. Now, A will depend on these parameters. And of course, when you integrate, you will get a constant of integration, which will be another parameter. So A will typically, of course, dependent on time, but it's dependent on a set of parameters alpha, right? And when we say that I change A at a given time, we are interested, so everything is at a given time. So this delta will be proportional to the variation of A with respect to these parameters. So we are interested in this del A, del alpha, where alphas are the, and this is the beauty of this method. So we are mapping this entire thing into a problem of a variation in A as A depends on its parameters. Okay, so that's the interesting way. Okay, now we can immediately write this down. So this can be integrated. Okay, so instead of writing this H0 and omega and all of these things, we'll just write, and you can integrate this, right? So we can take a square root, it will be some function, and you have a dA dt equals to some function of A, right? So we can write this down finally as dA dt as some function of A. So which we can integrate very in a straight of a manner. So you can have write t over here, and you have an integral 0 to A dA prime by, I mean, the way which is just some h function of h, right? So we write this quantity, whatever you have here, as x to the power half. And then there's a constant of integration c. This x to the power half is related to h of A. It's basically h. And then it's x will depend on the omegas, right? Now, of course, there are two omega m plus omega lambda must be 1. So there is essentially one parameter here and one parameter is c. So you have one of the omegas and one parameter is c. Okay. So what we're interested in, so my delta is finally proportional to 1 by A del alpha, where A is a function of these parameters. Great. So what we need to do is we need to find this del alpha. So here we have two parameters, omega, say omega m, one of them, and other could be this constant c. And then you have to just differentiate under the integral sign, which is not difficult. So you first say, let's say the first parameter is c. So we want to do del A del C. So you differentiate with respect to C at a given instant of time. So you have 0 equals to, you have to integrate this with respect to C. So you just have this integrand will come out at evaluated at A. So 1 by x to the power half and then you have del A del C, the upper limit, and then this will be 1. So from the first, you get del A del C equals to x to the power half minus, the minus sign doesn't matter because an overall sign. So your first solution, delta, you can write it as delta 1, is 1 by A is proportional to, let me write proportional to 1 by A x to the power half. This x to the power half is basically h. You know that from this, right? So that's the first solution. We already know, and this is not the growing mode, this is the decaying mode. To find the other solution, we have to differentiate this respect to one of the omegas. So let's say one of the omegas. So if you do that, so the second parameter, so say omega, and then you differentiate again, you have 0 equals to, now you have to differentiate this equation with, so now you have an x which is dependent omega, so you have to differentiate this. So one term will have the integral. So the first term will be an integral 0 to a dA prime x to the power 3 by 2 minus half, of course, will come out. And the second term will be plus so we are, this del C will be 0, but there's going to integration going to term will come from the upper limit of the integral. So you will have the integral, which is 1 by x to the power half integrand, and then del A del omega. So my delta 2, which is proportional to 1 by A del omega, this will now be x to the power half by A so this, and then there's this integral 0 to A dA prime by x to the power 3 by 2. So you have these two solutions, delta 1, which is 1 by A x to the power half, and delta 2, which is x to the power half by A, and then 0 to A dA by x to the power 3 by 2. Great. So exactly the same answer. This is nothing but h, and this is h times integral. You can convert it to dt, so you get exactly the same thing what we got in the morning, dt by a square h square. So another way of obtaining the same solutions, but please understand that this quadrature solution for the growing mode is completely inapplicable when you have radiation. So please don't use it generally. So only when there's dark matter and dark energy, you should be using this formula. It's very useful because it's just a numerical integration, and it gives you the growing mode just by a simple integration. But if there is radiation and other stuff present, then you have to actually use Runge-Kutta or some other numerical methods to actually numerically integrate this equation. So this is the equation, but you can always numerically integrate and get the growing mode. But if you only have dark matter, non-relativistic matter, and dark energy, then you can get the decaying mode, which is just proportional to the Hubble parameter, and the growing mode, which is given by this integral, a quadrature. So now we know how to at least do this. Of course, in the general case, you have to solve the whole thing numerically, but at least for the simple case, it is doable. Now let's do some example let's work out some important results for the growing mode. So let's work with a matter-dominated epoch. In a matter-dominated, and let's say we are looking at lambda equals to 0 solution. So no dark energy. It is spatially flat. So k equals to 0, and there is no pressure, of course, p equals to 0. So our equation is delta dot dot plus twice delta dot h equals to 4 pi g rho delta. So let's see what, now you know h. because in this matter dominated epoch, you know that A of t, how it scales, it's proportional to, so this is some, okay, let's write proportional to t to the power 2/3. This is something which you know from background cosmology. So you can immediately see that this h will be 2/3 t, and then you can just write this down. So you have delta double dot plus 4/3 t delta dot equals to, there's 1 by a square, so this rho goes as rho 0 by and you can write that down as in terms of omega matter, which is 1 now. So if you write this as omega matter, so you have to divide by rho critical. So you divide it by rho critical and you multiply it by 380 square by 8 pi g, and rho is rho naught by a cube. So this becomes omega matter, which is 1. So so you are basically a factor of 3/2 h naught square, and there's an h naught everywhere, so I'm not writing that. So you just basically have 2/3 t square delta. Great. So with that, you can just want to find a solution. This is particularly easy, and that's why I've chosen this as a very sort of a textbook problem. Definitely not the most general case because you have only a pressureless matter and no dark energy. But let's try to find a solution to this. So you can take, for example, delta, take a trial solution. You can take delta to be some, say, power law, so a t to the power n. And if you substitute, then you will get some quadratic equation with n. And I'll not do the algebra, it's very simple. So you will get 3n square minus n plus 4/3 n minus 2/3 equals to 0. Or when you solve it, you get two values of n equals to 2/3 and n equals to -1. So you have two solutions. So delta of x t will be t to the power 2/3 times some a of x and then some b of x t to the power -1. So this solution is what is called, now we know why it's called a growing mode. It grows, it's t to the power 2/3, and this is the decaying mode. So it's basically t inverse, right? H. So you know that H is 1/t. So it's expected that your decaying mode will be 1/t. And then there's a growing mode, and the crucial thing is that the growing mode, which sometimes is written as d plus, so the d plus is proportional to a of t. So a goes as t to the power 2/3. So the growing mode for cold dark matter in the matter dominated epoch with no dark energy, it's very simple, it just scales as a. In fact, it will, even if lambda is not, you can do the, so now I urge you to actually find this growing mode by solving the integral. So you can actually do that integral and see what you get. So that I leave as an exercise. Okay, so this decaying mode is not usually considered because whatever fluctuations decays will not participate and it will just quickly die out. This a of x takes care of the spatial dependency of this fluctuation, and we shall have a lot to talk about what kind of a quantities a of x is going to be. So right now we are interested only in the time evolution in the linear theory. So that's what we are. It's a very simple case. I mean, this is something which you should get at the back of your mind, that in matter dominated epoch, the matter fluctuations, they grow as a. Very important. Okay, so the next thing we want to study is the other quantity of interest, which is the peculiar velocity. Now, that's going to be of some importance to us. And the first, look at the growing mode, for example. So if you have a growing mode, so you have delta x of t is some a of x, and then there is d plus of t, right? So if a fluctuation is growing like this, then you can immediately see that delta t this will be positive. And if you remember your perturbation equation, then it would immediately mean that divergence of V, which is the first perturbation equation, this will be less than 0. So it would immediately mean when a divergence of vector field is negative, it means there's a matter inflow. So that's when as the perturbation grows, so there's an accumulation, there's gravitational assimilation of particles, and the fluctuation is growing at a point. You would immediately have the peculiar velocity field to be inward directed, so there will be inflow of matter, and likewise there would be matter flowing out if this is negative. Okay, so now let's focus on the peculiar velocity, and before that let's look at the Poisson equation. Okay, so let's go back to the Poisson equation. So we have already used it as a source on the right hand side. So if you see the general form of this equation, so you have this term on the right hand side which is sourcing the growth, and that is given by the gravitational potential, and we have already used the Poisson equation, but let's study it in some details. So we have the Poisson equation, which is given by del square phi equals to 4 pi g a square rho bar, and we are only interested in dark matter as of now, so dark matter. Okay, so let's do something first. So let's define a new quantity. Let's define a quantity which we call, say, have to introduce a new symbol. Let's call it xi. So we'll define a xi as this is just a definition. So let me write definition. Xi equals to. By the way, instead of writing this with a rho bar, it is convenient to write things in terms of omega, and we'll do that. First, let's define this xi. So xi can be defined as 2/3 1 over h naught square omega m0 a by the growing mode delta. Sorry, let me introduce. This is we are using symbol. So this is the phi. So we have just used a new variable, which is just related to this gravitational potential. Please remember, this is a fluctuation in the gravitational potential, and we have just defined it. So now this quantity itself is supposed to be something which depends on everything. So it has a spatial dependence coming from phi, and it has a and d. D is only the time part of the density fluctuations, and you have then these constants. It's just a definition. Now, if you apply the Poisson equation to now, so you will have this equation del square, the Laplacian of xi is 2/3 1 over h naught square omega matter a by d del square of phi, and we substitute from here. So we have 4 pi g a square rho bar delta dark matter. Now you can simplify. So this rho bar can be written as 0 by a cube. That's the first thing you can do. And then you can write divided by a rho critical and multiply with 3 h naught square by 8 pi g. So what will you have? You will have 4 pi g over 2, and this will be omega matter. So you will have a lot of cancellations, and finally everything will cancel. And that's why we had defined it this way. This was known to us. So we have del square of gamma, which will be now just delta very interesting. I mean, it's all concocted in such a way to obtain this quantity. Okay, now this is a Poisson-like equation, except the interesting thing is that we just saw that this the time dependence of this quantity, right, is just going to cancel, right? Because this grows as d, and this is something which is t. So the time dependence part will cancel, and you would have this del square gamma to be essentially a constant. So this is something which you have to keep at the back of mind. This del square gamma is something which is not changing with time. That's just by construction. So let me write this down. So delta dark matter, which of course has a time part and a space part. This is then D, which has the time part, and del square gamma. This has all the space part, because this does not have any time, and as we can see from here. Great. Okay, now let us, there's a reason why we're writing this, which will become very useful for us. So let's write down the equation for the fluid again. We go to the first equation involving the dark matter over density. So you have delta dark matter dot plus 1 over A divergence of V. Now everything is for dark matter. This is 0. So I'm not going to write the dark matter suffix. So, so what do you have? So you substitute this over here. So you have D dot del square gamma, and this has no time dependence, so this del square gamma, plus 1 by A, and we have divergence of V, that is equals to 0. So you can take one of these Laplacian operators outside, and then you have basically divergence of A d dot grad of gamma plus V. Great. Which means we have constructed a vector field which is divergence free. Now you know that when a vector field is divergence free, you can basically write as the curl of something, right? So this entire quantity within brackets would be the curl of something. So let's write that down. So we have A d dot gradient of gamma plus V dark matter. This must be equal to some curl of some vector field A, and which in other words means that V dark matter can be now written as minus A d dot gradient of gamma plus curl of. Now this, if you are familiar with vector calculus, this is basically the Helmholtz theorem, where we are splitting a vector field into a divergence free part and a curl free part, right? So this is the divergence free part, and this is the other part. Okay, great. So this split is natural, so we can always do that, except that we know what this quantity is now. Very good. So what we want to do is we want to write this velocity. We can call this curl of A as V perpendicular, and then we can substitute this back to the fluid equation. Okay, so instead of so we have used the first equation. Let's substitute this in the Euler equation. So the perturbed equation was V dark matter dot plus H V dark matter. Sorry, there's no dot here. Equals to minus 1 over A gradient of phi, right? Now this we already know how to write in terms of this xi, in terms of gamma. So you have 1 minus 1 over A, 3 H naught square by 2 omega m0 d by A grad of psi. So this is something which you have just from definition, and then you substitute for V this quantity. So what will you have? You will have several terms because you have A, D, except that this grad of gamma is something which is time independent. We saw that. So you have several terms. So this derivative will give you what kind of terms will you get? Let's actually do it. Let's work it out. So you will get when you take the derivative, you will get minus a d double dot grad xi minus a dot d dot grad xi plus v perpendicular dot plus a dot by a, that is this term, I'm doing this term now, a dot by a v perpendicular minus a dot by a d dot grad gamma. Now we have written everything, and on this side we have if you write, so it's minus 1 over a square 3 h naught square by 2 omega matter naught d grad xi. Okay, so there would be many cancellations. So this a dot d dot term, this a cancels. So this and this together gives you a minus twice a dot d dot grad gamma, right? And then if you remember, we have already written this expression. Where did I write? Just a minute. Right. So you can use the expression for d dot, which is known to us. So let me again write this down. So you have minus a d double dot grad xi minus 2 a dot d dot grad xi plus v perpendicular dot plus a dot by a v perpendicular equals to minus 1 over a square 3 by 2 h naught square omega m d grad gamma. So this term, and this term cancels altogether because that's basically the equation for d plus d, and you are left with that's just the equation for d plus. Right? You divide it by a, you just get that, right? So that's the exact same equation for d, and you can. So this term cancels with these two terms together, and then you are left with this very important result: v dot plus a dot by a v perpendicular is 0. What it essentially means that this v perpendicular goes as 1 over a. Because v dot by v equals to minus a dot by a, so v goes as 1 over a. So this is very important. So what is crucial here is that you see this was the curl term. V perpendicular was some curl of a, right? So this term actually has to decay down. So this, you start with whatever term of the form of a curl, right? So this term will eventually die down. It will not have it. So you will only have this term, which is the curl free term, this divergence free term, which is curl of a, which will disappear. So v dark matter will then be just a term which is curl free, because the divergence free term, which is v perpendicular, this term, we have just shown that it decays off. So even if you start with something which is having a curl, so the divergence free term, that will decay. So that's similar to the question also. If there are vector perturbations which has a curl, which is a curl of something, that will actually not contribute, it will decay. So it immediately means that if it's curl free, so we can introduce what is called a velocity potential. So this is a curl-free vector field. So we introduce what is called a velocity potential. So then V dark matter, which you write as minus A d dot grad of gamma. This is basically, you can immediately say this is basically gradient of some scalar, and the time dependence is in this term. This is essentially time independent. Okay, so if you have written this velocity in terms of just the potential, gradient of some potential minus grad of some quantity, so that is just like, you know, electrostatic field. I mean, and you can now write down, and you know, this del square of gamma. This is related to the Fourier. Sorry, this is related to the Poisson equation, not the Poisson equation. So you can immediately make that connection, and you can write a Poisson-like equation for this this quantity, and try to at least write some kind of a solution, at least a formal solution. So what will that formal solution be? So so this entire quantity we call psi velocity. So we just write this velocity as minus the grad psi velocity, and then you can just talk of
Hi, Tapomoy, can I ask
yes.
a question?
Yes.
Yes. So this curl terms, how fast does it decay, and for different epochs of the universe?
So this which term? This term. V perpend this dot equals to minus V A dot by A.
The call term.
So the other term, right?
Yes.
So the term, this term. There's a divert. This term is a curl of some vector field which is divergence free, and then the other term is curl free. So the curl free term stays. In fact, the curl free term grows, as you can see, right?
Yes.
How will it grow? It will grow as A times D dot.
Sorry, the question is the curl, how fast the curl term decay?
You are asking how this equation is coming?
No, how fast the curl term decays.
Yeah, so the curl term is V perpendicular, right? This is the curl term, curl of A, that I'm calling as V perpendicular. This term, curl of A, we are calling it V perpendicular, which is divergence free. And V perpendicular satisfies this equation, V perpendicular dot equals to minus V perpendicular A dot. Yes.
Oh, yeah, I was not able to unmute myself. So I was asking how fast this term decays for different like matter-dominated universe or radiation dominated.
It'll decay as 1 over A.
For all cases.
Right? For pressureless. Everything is for pressureless, for dark matter.
For dark matter,
CD.
but for okay.
Yeah, A you can solve. Yeah, you can have other stuff. So A you can solve for that background, and you know how A goes.
Right. No. So how fast does it decay with compared to the Hubble time? Or
yeah, since it is falling off as 1 by A, since it's falling off as 1 by A, right? If you look at this velocity is always slower than the density. So that is what we are going to show. It falls also. See, how does the decaying mode for density goes? It goes as 1 over T, right?
Yeah.
But but A goes as T to the power 2 by 3. So A goes as T to the power 3. So you can look at how that goes. So, but the crucial thing is that they decay. What is crucial, more important is this term, which is the other term, which has A d dot, the time part. So V dark matter, finally, the other part is A d dot. So it is actually going to grow, but it is going to grow slower than the than density, which is of paramount importance. That dark matter grows as A, as we just saw, but the velocity perturbations, they are slower. They grow slower. Because you can compute D is proportional to A. So A dot will be, and A is some T to the power 2/3. So this will be some T to the power some power which is less than 2/3. So this will grow slower. So the growing mode is going to grow slower than the dark matter growth, which is crucial. Now, what is sometimes what you do is you can write this as this del square. So what you typically do is you write this instead of D dot, which is not very convenient in cosmology, you introduce this quantity F. So which is D in logarithmic growth, so derivative. So D log D and D log A. So this is a standard thing of use in cosmology. So just expressing in log, because A is a very bad unit to use. I mean, so just logarithmic, it's good. So so in terms of this F, you can immediately see that this del square psi will be, you can write this as, which is basically A. I can introduce minus, I've already introduced. No? So del square psi will be A D dot, then instead of delta, so this you can write, I'm just going to make the conversion, okay? So that is convert A D dot, you divide it by D, and then you might write it as delta, which is now X and T, the full delta, and then you convert it to log. So this is going to be, let me see, it's going to be A, you take an A, which is remaining, and take an H, F, and then delta xt. So this is the standard form. So basically have a Poisson equation. And F is this logarithmic growth rate. And you can now actually write a solution, at least a formal solution. So you can write this psi x of t. And this is just now Poisson equation. So you can write this as minus a.
Hello? Hello?
Yes.
Hello?
Yes, I can do it.
Actually, I want to at your starting of the lecture, you said that the original idea system has dark matter and dark energy, and the system is specialized. Hello? Am I audible? Hello?
I could not hear. Can somebody, I mean.
Hello? Hello?
Yes. Yes. What is the
Hello?
question?
At the starting of the lecture, you said that we consider the system is specialized, right?
Yes. Yes.
It has only dark matter and dark energy.
Dark matter and dark energy. That's all we have. Yes.
Yes, and dark matter is specialist, but how we consider the dark energy is specialist? Because from standard of we know that dark energy has a negative pressure. So the open system may have a negative pressure.
But it has no perturbations. So it has no perturbations. So we are not talking about clustering dark energy. And it is, yeah. So it has an equation of state. That is fine. But I'm talking about matter. In the matter sector, I'm not talking about. So I'm not considering equation and baryons.
Okay. Okay.
Yeah. So yeah.
Okay. Thank you.
But the point is, this is, we're doing everything pretty much in the dark matter dominated regime. So you really don't have to worry. So this is actually rigorously correct in the case where lambda, everything is 0 and you have only dark matter. So we are just talking about dark matter. I think in the presence of lambda, you have to just change the background equations. Okay, so Is the screen visible?
No, it has disappeared. Can you unshare and share it again?
Is it visible now?
Yes, yes.
So you can now just write a solution to this, just like you have for your electrostatics. So then you have this integral x prime t d cube x prime divided by x minus x prime. So it's a formal solution, and then your velocity, which will be the derivative of this, you will have basically, you can write it just like you write the electric field from a potential. So you can give an expression for your velocity. Just a standard formal way of writing it. So if you know this, the source, so you can now, so the peculiar velocity field is now completely sourced by the dark matter over density. So if you have a dark matter over density, you can have the peculiar velocity field sourced by it, and you can formally integrate this and get the peculiar velocity. Okay. So about the question which was asked, I think this entire analysis is about things which has no pressure. So let's not keep dark energy or anything as of now. So this is just entire analysis is for just dark matter. I think that would keep it straightforward, because yeah. So if there is any source of pressure, this analysis is not going to work. So we have a universe which is matter dominated with only dark matter, cold dark matter. So that's when this analysis is true. Okay, so that's why we are getting the velocity field is just sourced by dark matter. So there's nothing else. So we have a dark matter over density, and that is sourcing the peculiar velocity field, and the expressions are given by this. Okay. So we know now at least how to do the entire thing for dark matter. So that's what I wanted to say. At least for dark matter, and the solution to the equation which we obtained, for example, here. This also did not have any cosmological constant, because you could straight away write this A of t. But of course, this is going to work perfectly fine in matter dominated epoch, right? When that omega lambda is going to be subdominant. And this solution, this quadrature solution is going to work for universe with matter and dark energy. You don't have to, but you cannot have radiation. So it will it's going to be perfectly fine with omega lambda and omega matter. Yeah, so let me be cautious here and see what the limitations are. Okay, so essentially we have done the basic things for dark matter. So we know how it evolves, dark matter perturbations, and how peculiar velocities behave when there is a dark matter over density. So it essentially it grows slightly slower than the dark matter perturbations, and that is very important, because when dark matter perturbations become nonlinear, your velocity perturbations may not be nonlinear. So it may still remain linear. It's not growing that fast. And this, if this weren't so, we wouldn't be able to use what is called the Zeldovich approximation. So even when density fields become nonlinear, the velocity fields still remain quasi-linear, and one can still do some quasi-linear analysis there. So we'll do that almost like quasi nonlinear domain, which is what we study in what we call the Zeldovich approximation. So there we will see that the fact that the velocities don't become nonlinear while the dark matter does is going to allow us to do that. Okay, so now we come to dark matter and baryons. Okay, so since we have been speaking about baryons, So let's see what happens when you have baryons. So with baryons, first thing to note is that now we would have to put the pressure term, and that would lead to an entire new physics, as we shall see. Somehow the screen has disappeared.
Yes, we cannot see your screen. So
What is wrong?
there is
Why
only 5 minutes left.
Yeah, so I'm going to just make one point about this,
Okay, so
and we'll continue.
try yeah, answer and say, yeah, it's working. Yeah.
Okay, now it's coming. Okay, good. So now when we start to look at baryons, we first note that, of course, now you have to keep the source term on the right hand side, which has the pressure. So we write it down as delta dot dot plus twice A dot by A delta dot equals to del square P by rho bar A square plus 4 pi G rho bar delta. So this is what comes about now, and we need to somehow relate this pressure to the density. Okay, so what we'll do is we will define the sound speed c square. So if there is a fluctuation in pressure, it will lead to a fluctuation in density, and you define this c square, the sound speed, as del p del rho, and we'll write this as this dp that you have. This is, remember, this is actually dp, the pressure perturbation, which we have written as small p. This is just c square delta rho. So you can now translate this equation as delta dot dot plus twice A dot by A delta dot equals to C square by A square, and then there's a del square, sorry, del square delta plus 4 pi G rho bar delta. So now the crucial thing is that this delta over here, if you're writing for baryons, this will still be dark matter, whereas these will be baryons. And that is the crucial thing. So on the right hand side, you still have the dark matter fluctuations, which is sourcing the whole thing. And this pressure is coming from, term is coming from the baryons. And of course, we are writing the fluctuations for baryons. Now, very good. So we will continue the next class, but let's just finish with one thing. Now, you already have seen that this Hubble expansion term, A dot by A, this is like a dampener. Now, if you see, if you forget this source, you can see this is already looking like a wave equation, something with a 2 time derivatives minus something with a space derivative, right? So if you remember, the wave equation is something A dot dot minus, sorry, on the other side, C square, and this is equals to 0. So this is like a wave equation, right? Now you see this is exactly like a wave equation because you have this Laplacian, the 2 space derivatives and the 2 time derivatives here. If you bring it to this side, this is like a dampener and this is like a source. This is like a damped wave equation in the presence of a source. So that's what the physics is about. So we have to understand what happens to a damped wave equation, which means that the wave is trying to has a tendency to oscillate, and then there is a dampening, and then there is also this inhomogeneous term on the right hand side, which is acting as a source, which is trying to grow the perturbations. So while there is gravitational instability, which is trying to grow the perturbations, as we just saw for dark matter, there is this Hubble term, which is like a dampener. It's trying to erase the expansion of the universe, which is trying to erase. And now we have another contribution, which is the pressure support of the baryonic gas, which is also opposing this structure formation. So there's an interplay of these 3 things: gravitational instability trying to grow the perturbations, then there is pressure, which is trying to oppose it, and then there is, of course, cosmic expansion. And the interplay of this is, now this equation, now CS is a function, everything is a function of time over here, and it's a very, very difficult equation to solve in the general case. I mean, it might look pretty simple, but this is actually the source of a baryonic physics. So it's actually very, very tough to solve this numerically, putting all the evolution, because the CS, the sound will depend on various thermodynamics of the gas, for example, temperature, etc. And you have to write the equations for the evolution of all that, because you have astrophysical properties of the gas which will come in, and they will all affect this thing. And you would have a very complicated set of equations. So if you write all sorts of equations involving all the time evolutions, it would be a very difficult numerical problem. But what we shall look at is very general properties on very large scales, which will allow us to point to the necessity of numerical simulations one, and on what kind of simplifications we can draw on those large scales. What can we say about baryonic physics at the distribution of baryons and the growth of perturbations of baryons on very large scales. So we'll start in the tomorrow with this thing. So we'll start with what is called Jeans theory of gravitational instability, and we will see at least we will see in some restrictive cases we can make some statements based on analytic calculations about how the baryonic fluctuations will depend on the dark matter fluctuations. We'll make some heuristic assumptions, and then we will go on to fluctuations on the spatial surface. So we have only talked about time evolution today. So after we finish with this, we will go to the spatial description of fluctuations. So I'll stop here if there are any questions. So in the analysis for the peculiar velocity, we have dark matter, which is sourcing the peculiar velocity, and dark matter over density creates peculiar velocities, which are essentially, you can show that the term which is divergence free dies down. It has only a curl free term. So you can always express the velocity field, the peculiar velocity field, which is sourced by over densities of dark matter. They are always going to be expressible in terms of a velocity potential. So people just use this velocity potential, but you have to argue that if there was a term which was not of that kind, it had a curl, then that would actually die off. So that would not contribute. So we can safely use this velocity potential, and it's always convenient to use a potential because it's a scalar, and then you can take the velocity. So that was the analysis. Any questions about anything that we did today, the whole 2 lectures?
Thank you, Tapomoy, Sarkar, and now the time for questions. You can now unmute yourself. So please go ahead and unmute and ask. There is a question in the chat box. So the Fajlu asking for references. Can you please suggest some reference?
So most of this is from the book by Peebles, this Newtonian perturbation theory. The best source is the book on structure formation by Jim Peebles. For relativistic perturbation theory, there is the famous review by Bershinger. I have not done any relativistic. Bershinger has a review, Mukhanov has a beautiful review, and of course Weinberg's book is there but that is all relativistic perturbation theory. So for Newtonian perturbation theory, the best reference I think is the book by Peebles, which has details of some of these topics. There is no better book than that.
Okay, thanks. I don't see any hands raised also. All right, if you have any question, you can also put it in the Slack. So let us thank Tapomoy Guha Sarkar again, and we'll resume this set of lectures tomorrow. And before that, we have a tutorial by Avinash Kumar Shah from IIT Kharagpur, and he will be discussing the numerical aspects. So how can you solve this large-scale structure of the universe numerically using n-body simulation and different numerical tools which is used to analyze these things. So now I would like to request Avinash Kumar Shah to please share his screen and start his tutorial.
Can you see my screen? Hello.
Just a second, Avinash, please.
Yes.